Good afternoon, everyone. Welcome to my talk. My name is Jiayi Lian from Zhejiang University. Today I will present our work titled A Nearly Quadratic Time FPTAS for Knapsack. This is a joint work with Chen, Mao, and Zhang, also from Zhejiang University. In Knapsack, giving items with specific weights and profits, and a knapsack with a certain capacity T. The goal is to choose items that maximize total profits without exceeding the knapsack capacity. This problem is well known NP-hard. In our paper, we focus on approximation schemes for solving it. Specifically, we study polynomial time approximation schemes, or PTAS. For any instance, our goal is to find a solution where the total profit is at least 1 minus efficient times the optimal solution profit in polynomial time with respect to the instance size and 1 over efficient. In this table, we summarize some results on this problem. The best algorithm so far runs in n plus 1 over efficient to the power of 2.2. Assuming the mean plus convolution conjecture, there is no algorithm better than quadratic time. Our work closes this problem. Notably, Xiao Mao has also developed an algorithm that runs in quadratic time. Okay, let's start with an important definition, the value function. Let I be a set of items. We define its value function as follows. For each capacity y from 0 to t, the value of the function is the maximum profit we can achieve, with a total profit not exceeding y. It's easy to see that our goal is to approximate the value of the function at t. To compute the value function, a basic method is grouping and merging. Suppose we divide the set I into two subsets, I1 and I2. And we know the value function of this subset. Then we can compute the value function of the entire set by using the max plus convolution. The idea is that we try to determine the maximum total profit by allocating capacities to I1 and I2. Although we only need the value at the total capacity, we must approximate the functions for I1 and I2 at all capacities to compute the correct answer at t. To approximate a function, there are two different parameters, the approximation factors and the additive error. Approximate with a factor of 1 plus efficient means that for each capacity, the difference between the approximate function and the real function is at most 1 efficient factors of the approximate function. On the other hand, the additive error delta means for each capacity, the difference between the approximate function and the real function is at most delta. The main idea of our paper is that if we know the optimal solution is at least b, then we can compute an approximate function with an additive error efficient times b, instead of aiming for a real 1 plus efficient vector approximation. And if we know that the value function of entire set is a convolution by the value function of I1 and I2, and the contributions of I1 is at most B1. We can just approximate Fi1 and Fi2 with half of the total additive error. This means the approximate factors of Fi1 can be larger than 1 plus efficient. By allowing a large factors, we can rescale the profits and make the process more faster. To plot the contributions of some items in the set, The key technology we use is an additive combinatorial result. It was previously applied in our exact algorithms for Knapsack. Let A and B be two multisets with a maximal elements denoted as P. If A has many distinct elements, that is, more than the square root of P, and the total sum of B is big enough, that is, more than P to the power of 3/2, then there exist subsets in A and B whose the total sum are equal. So how to use these results? We sort the items by the profit-to-weight ratio. Then we find the black item for the knapsack capacity. This means we start by taking the most efficiency item first, one by one, until adding another items would make the total weight exceed the knapsack capacity. Then starting from the black item, we pick items on both the left and right side. That it has a number of distinct profits equal to the square root of P. We let these items be I2, the items with high efficiency be I1, and the items with low efficiency be I3. Using an additive combinatorial, we show that the total weight of items in I1 but not in the optimal solution is at most P raised to the power of 3/2. And similarly for the items that are in 3 and also in the optimal solution. To see this, we consider I2 as A. There are enough distinct profits. If there are many items in I1 but not in the optimal solution, then there are subsets of I1 and I2 that the total profit is the same, and the items in I1 has a higher efficiency. Why wouldn't the optimal solution choose the items in I1? The key points to use these proximity results is to bound the maximal profit in the set. To do this, we partition items by their profits such that in each set, the maximal profit is at most twice the minimal profit. Then we scale the profits to 1/epsilon and round to integer. Then we scale the profits to 1/epsilon and round to integers. For each item, we round at most epsilon fractions of its profit, so the error is allowed. Then we get a reduced problem. In this problem, profits are from 1/epsilon to 2/epsilon. As we partition the items, the goal is to approximate the value functions at all capacity with additive error 1/epsilon. Now we can use the proximity results and partition the items to I1, I2, and I3. Then we approximate the value function of them and compute the convolutions to find the value function of the entire set. To approximate I2, we use the theorem from Chen. If there is n functions that we want to compute the convolution, and each of them are a value function where the items have the same profit, then we can approximate it with factor 1 plus epsilon in times n squared over epsilon. In I2, there are only the square root of 1/epsilon distinct profit. We can partition the items by their profits and merge them one by one. To approximate the value function of I3, the additive error we need is 1/epsilon, and since the contribution of I3 is at most 1/epsilon raised to the power of 3/2, the approximation factors can be 1 plus the square root of 1/epsilon. Then we can rescale and round. After that, it can be computed by standard dynamic programming in quadratic type. Is it end? No. As we said, we partition the items so we need to approximate the value function on all capacities. However, the proximity results also works for a single capacity. That is, using the proximity results, we only get a good approximations at capacity T. In other points, it's not always right. If we compute for all capacities, it takes too long. But that's an obvious since neighboring capacities have neighboring black items, so can then share the same partition. We need to pick items with the square root of 1 over epsilon distinct prefix from the black item both to the left and right just now. If we choose twice as many distinct prefixes, then the capacity in this range can share the same I1, I2, and I3. This way, we define the range from 0 to t into the square root of 1 over epsilon intervals. Since computing each interval takes quadratic time, it's still too slow to do them individually. However, there are some structures in these intervals. For example, I1 in a later intervals is always a subset of I1 in an earlier intervals. An I3 in an earlier intervals is always a subset of I3 in a later intervals. As we said, we compute I1 and I3 by standard dynamic programming. So by computing I1 from later intervals to earlier intervals, we can compute all intervals at once, and the same goes for I3. Then for I2, recall that we use chance theorem to approximate it. The key point is that we don't actually need a vector of 1 plus epsilon. Instantly, the contribution of I2 is at most the total profits in it, which is at most the number of items times 2 over epsilon. So similar to the previous analysis, the approximation factor can be 1 plus 1 over the number of items in I2. The running time of one interval then is the number of items in I2 multiplied by 1 over epsilon. Since I2 of non-adjacent intervals do not overlap, the total number of items in I2 is at most twice the number of items before the black item, which is at most 1 over epsilon. So overall, we can compute in quadratic time. Now let's summarize. The key idea is that in a knapsack, item sets with small contributions allow a large approximation factor, which makes us compute them faster. And most contribution comes from high-efficiency items, which are always in the optimal solution, so we can add them without error. We prove this by using a result from additive combinatorial. First, we reduce the problem to lower the maximal profits. Then we divide the items into 3 subsets and compute the value functions of each one. However, the proximity results only works for a single capacity, and we need to approximate the whole function. So we break all capacity into intervals. For I1 and I3, we compute all intervals at the same time, and for I2, we found that we allowed a large factors again and compute faster. Then we get a quadratic time FPTAS. Although we close the gap in this form of FPTAS, there is still some open problems about Knapsack. First, can we find an FPTAS running in n over epsilon time? Right now, in this form, the best scheme runs in either 1 over epsilon squares times n, or 1 over epsilon times n to the power of 3 halves. For the exact algorithm, there is an important open question. Can we create an algorithm that runs in time n times w, where w is the maximal weight. By the way, even though there is a conditional low-bound suggestion that we can't do better than n plus w squared, can we improve if we consider both weight and profit? Okay, that concludes my talk. Thank you for your attention.